Hello everyone, and welcome back to the Fluctus Channel. Since its inception, the U.S. Air Force has remained deeply committed to developing aircraft that embody cutting-edge technology, often in response to major global events such as World War II and the Cold War. Even after those eras, innovation continued to thrive, leading to remarkable achievements like the B-2 Spirit, a multi-role stealth bomber designed to deliver both nuclear and conventional weapons. Developed by Northrop Grumman in the 1980s under the Advanced Technology Bomber Program, the B-2 brought together the expertise of several industry leaders, including Boeing, Hughes Radar Systems, General Electric, and Vought Aircraft Industries. It was officially unveiled in 1988, representing the culmination of decades of research into stealth technology that began with laboratory experiments and aerodynamic design studies. The foundation for the B-2's distinctive design was laid in the 1940s and 1950s, when Northrop developed pioneering flying wing prototypes, like the YB-35 and YB-49. These early aircraft demonstrated the aerodynamic efficiency and low radar visibility for the flying wing configuration. In the 1970s, Northrop further advanced stealth technology with the Tacit Blue experimental aircraft, developed under the Stealth Aircraft Technology Program. These efforts directly influenced the final design of the B-2 Spirit. The production of the B-2 Spirit marked one of the most complex and secretive aircraft manufacturing efforts in U.S. history. After years of design and testing, Northrop Grumman established a specialized assembly line at its facility in Palmade, California, known as Air Force Plant 42. This high-security site was equipped with climate-controlled hangars and advanced composite fabrication tools capable of handling the bomber's massive, curved flying wing structure. Each B-2 was built using precision manufacturing techniques that combined traditional assembly methods with new automated systems for laying radar-absorbing composite materials. Engineers and technicians worked under tight compartmentalization, with different teams assigned to specific classified tasks to preserve secrecy. Boeing handled major structure components and systems integration, while General Electric supplied the powerful F-118 GE-100 engines that gave the B-2 its smooth, low-noise profile. Production took years for each aircraft, as every surface required meticulous shaping and coating to ensure radar invisibility. Quality control was relentless. Every panel, fastener, and seam underwent extensive inspection. The final assembly phase included calibration, systems testing, and flight validation before delivery to Whiteman Air Force Base. Though only 21 B-2s were produced, the line represented a monumental achievement in aerospace manufacturing, combining stealth, precision, and craftsmanship at a scale never before attempted. The Spirit's distinctive flying wing design sets it apart from any other aircraft in service. Unlike conventional bombers, the B-2 lacks a traditional tail or fuselage, resulting in a sleek, blended body that integrates its wings and main structure into one continuous aerodynamic surface. This configuration greatly reduces drag and radar visibility while enhancing lift efficiency. Despite being shorter in overall length than most bombers, the B-2 compensates with an impressive wingspan of 172 feet, roughly the width of a football field. This enormous span has a direct impact on the facilities used to house and maintain the aircraft. Standard hangars simply cannot accommodate its size or specialized maintenance requirements. For this reason, the U.S. Air Force constructed purpose-built shelters designed specifically for the B-2. These hangars are typically more than 200 feet wide, allowing technicians unrestricted access to the wingtips and control surfaces for inspections, repairs, and refueling operations. Moreover, these structures are not ordinary storage spaces. They function as climate-controlled environments that protect the B-2's sensitive radar-absorbing materials and electronic systems. Maintaining stable temperature and humidity levels is essential to preserving the aircraft's stealth coatings and ensuring the integrity of its advanced composite skin. Each hangar essentially acts as a secure maintenance ecosystem for one of America's most secretive flying machines. This location is where most pre-flight procedures are followed when a mission is about to start. First, the pilots must attend a mission briefing where they review the mission objectives, as well as the weather conditions and the equipment they will use. Meanwhile, the maintenance squadron, located in the hangar, is responsible for loading the ammunition using advanced tools that speed up the process and reduce the risks of failure. Once the ammunition is ready, other squadron members carry out checks on the plane alongside the pilots, who follow pre-flight procedures inside the cabin. Finally, the ground crew and air traffic control start guiding the plane through the runway, where the pilots will take off. While flying, the B-2 shows why it has revolutionized stealth operations with its incredible capabilities. Considering the path that the B-2 has opened for new developments in stealth aircraft, in recent years, it has focused on the design and creation of a new aircraft, which is considered the evolution of the Spirit. The said plane is the B-21 Raider, part of the stealth bomber 6th generation family, designed to be the backbone of U.S. strategic air power for the coming decades. With innovation in materials and manufacturing techniques, the B-21 is built to evade even the most advanced anti-access area denial systems. Like its predecessor, the B-21 can deliver both conventional and nuclear payloads, supporting a range of munitions from standoff weapons to direct attack systems. Being shown to the public for the first time in 2022, the B-21 began its testing flights in November 2023 to demonstrate all its capabilities in different climatic conditions and execute missions. Test flights are conducted as frequently as twice per week, showing the program's progress in reaching a steady and reliable test cadence. In recent decades, this explosion of innovation around stealth technology has created various designs, including the F-35 Lightning II, the latest 5th-generation fighter. Designed to replace a multitude of aging fighter aircraft across various branches of the U.S. military and allied nations. The F-35 represents next-generation technologies aimed at maintaining air superiority in modern combat environments. Its development began with the Joint Strike Fighter program, whose system development and demonstration phase ensured the F-35 could obtain initial operational capability. In addition, this project has collaborated with 9 countries seeking to improve their air capabilities. This collaboration has fostered interoperability among allied forces and distributed the economic and technological benefits of the program among multiple nations, enhancing global defense capabilities. An aircraft of this complexity involves equally complex manufacturing, so Lockheed Martin must use innovative processes and cutting-edge technology to create this aircraft. Being a modular design, different contractors are in charge of building the various sections of the plane and then assembling them in a specialized facility. Northrop Grumman is responsible for producing the center fuselage through an integrated assembly line consisting of automated work cells, optimized for precision and speed. Digital twin models are used throughout production to optimize assembly steps, ensuring accuracy and minimizing waste. Other assembly enhancements include using augmented reality projection technologies to improve precision and efficiency. This is the case with the calibration with projection work system, which uses CAD model data and projects it directly onto physical components, guiding workers during fastener installation. With similar processes and equally advanced technology, the other suppliers are responsible for completing the remaining sections, with Pratt & Whitney being in charge of building the F-135 engine and BAE Systems producing the aft fuselage in the UK. This last contractor is in charge of the structural test of the CTOL airframe at the Structural and Dynamic Test Facility in the United Kingdom. BAE Systems follows this process to validate the structural strength of the airframe and determine if it can be maintained throughout its operational life. They perform fatigue tests, simulating long-term wear and tear by applying cyclic stresses in an established time frame. The resulting data of this test is used to detect potential issues like cracks or other service-related conditions. The same goes for the static test, which analyzes the airframe's response to peak loads and ensures that structural limits are not exceeded. Once the data is gathered and the structure is considered safe, it returns to the U.S. to complete its assembly. To complete the construction of the F-35, workers must dedicate themselves to installing the aircraft's electronic and avionics systems, including innovative technologies such as the electro-optical guidance system. Thanks to this tool, F-35 pilots can have better surveillance and guidance capabilities through a combination of laser point tracking and infrared sensors. By connecting those tools to the aircraft's avionics, technicians enclose the EOTS within a sapphire window in order to protect the sensors, but reduce aerodynamic drag and maintain the F-35's stealth. Once the entire structure is installed and the systems integrated, the engineers proceed to continue with the different tests to verify the functionality and characteristics of the F-35. For example, at Lakenheath Air Base, acoustic emissions tests are carried out, determining the noise levels produced by the aircraft and determining whether the shelters can accommodate the F-35A's unique engine sound, thrust, and exhaust profile. At another location, the aircraft is placed inside a climate chamber to evaluate the operation of the aircraft's systems under extreme heat, cold, rain, and humidity conditions. With the functionality of the internal systems of the aircraft verified, the military forces proceed with external tests that include flight, use of weapons, and even landing. Here, we seek to test the most difficult conditions, such as landing on snow, to determine the behavior of the wheels in this terrain and the ability of the pilots to react to this environment. Behind this type of test is also the logistics to maneuver the planes on the runway, in addition to being able to transport parts and equipment between hangars to be implemented in the F-35. The continuous emergence of new technologies and manufacturing methods to give birth to stealth aircraft has proven its great importance for air forces worldwide. The momentum these advances have had only highlights the air superiority of aircraft such as the B-2 or the F-35 and marks a clear path for the appearance of new aircraft that surpass the current generation. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.